In hypothesis testing, we can adopt this 7-step procedure to complete the testing process. The first step is to propose or set up a null hypothesis and an alternative hypothesis. A null hypothesis is a hypothesis that we put into test directly, often with an intent to reject. An alternative hypothesis is the researcher's own belief. For example, a researcher believes that the rising temperature is causing rising precipitation. So in other words, this researcher believes that there is a positive relationship between temperature and precipitation. To prove this, to prove his own belief, the researcher would set up a null hypothesis which states that there's no relationship between temperature and precipitation. So if the researcher can reject this null hypothesis, his own belief will be in favor, will be somewhat proved. So often we use this logic to conduct hypothesis testing. So null hypothesis often is set up with intent to reject. But that's not always the case. For example, sometimes you want to prove that your variable conform to a normal distribution. For that purpose, you would set up a null hypothesis that says that this variable conform to a normal distribution. And very often, you would not want to reject the null hypothesis because the researchers very often want to show that their variable conform to a normal distribution. Okay. Also, the alternative hypothesis can be non-directional or directional. When you have a non-directional alternative hypothesis, we are conducting so-called a two-tail test. When you have a directional alternative hypothesis, we'll be conducting a one-tail test. So we will have more specific to say about non-directional and the directional alternative hypothesis, and also about the two-tail test and one-tail test later when we do the in-class activity about hypothesis testing. The second step is to select the level of significance. This is to choose a small probability that we call alpha. The reason that we want to determine the level of significance is to set up a standard, a benchmark for a so-called rare event for the given null hypothesis. We said in the past that if a sample mean proved to be a rare event for the given null hypothesis, we would reject the null hypothesis. The question is, how rare has to be rare? Is that 10%, 5%, 1%, or lower? So the purpose of choosing a level of significance is to determine this small probability, to determine how rare is rare. The value of the magnitude of rareness is reflected in the level of small probability alpha. Now, different research communities often adopt a different level of significance because they deal with different research subjects which often require different levels of rigor. For example, for medical and drugs research groups, they often deal with life and death situations, so they really want to make sure that the drugs they invent and the medical procedures that they design truly have effect in treating some diseases and patients. So they really want to see the strong evidence so that they can reject the null hypothesis. The null hypothesis says that these new drugs or new medical procedures have no effect in treating patients, in treating diseases. So they really want to find some very strong evidence to reject this null hypothesis, so that they really, once they can reject the null hypothesis with at a very high degree of rigor, and that drug probably truly have effect in treating patients and in treating diseases. But for geography and for some social science areas, we do not really deal with life and death situations, so there's no need for us to adopt very a small alpha level. Very often we adopt 5%, 1%, so that's very often the case. In the past, there are researchers who adopt alpha at 10% level, but recently we don't really see many researchers still adopt 10% level. That is regarded as too, the standard is too low. So you need to adopt at least 5% level or lower alpha. Step number 3 is that after you decide the level of alpha, step number 2, you need to find out the corresponding critical values. And these are so-called, these are some z-scores or t-scores that correspond to the level of alpha that you choose from step number 2. For example, if in a two-tailed test, if the alpha we choose is 5%, the corresponding z-score, the corresponding critical z-score value would be negative 1.96 and positive 1.96. Now, these two critical z-score, we use these two critical z-scores to delineate entire z distribution into two rejection regions at the corner and one non-rejection region in the middle. The reasons that the rejection regions at the corners is that we know in a normal distribution, the events at the corner have a small probability to occur. So they are the rare events. Now those events that occur toward the middle have a higher probability to occur. So they are the non-rare events. Okay. So if any sample mean turn out to fall in the rejection region, fall in those two corners, then we know that they would be regarded as a rare event for the given null hypothesis, so we would have to reject the null hypothesis. And that's why that this region at the corner are called the rejection region. If, on the other hand, a sample mean fall in the non-rejection region here in the middle, then we would know that the sample mean is not a rare event for the given null hypothesis. So we would have no reason to reject the null hypothesis. And that's why here in the middle, it is called the non-rejection region. So these two critical values divide the entire z distribution into two rejection regions in the corner and one non-rejection region in the middle. Also, when you choose different alpha level, you can get a different critical value. For example, when you choose alpha at the 1% level, the corresponding critical values would be negative 2.58 and positive 2.58. So now you can really see that the rejection region, these two corners, become smaller, and the non-rejection region will become larger. Now for a particular sample mean, when you choose alpha at the 1% level, you would have a harder time to see that sample mean to fall in the rejection region, because now the rejection region becomes smaller. You would have a harder time to reject a null hypothesis. So a smaller alpha is regarded as a more rigorous standard. Now step number 4 is to calculate a test statistic from the sample mean. This is to convert the sample mean into a z-score or a t-score. The purpose to convert the sample mean into a z-score or t-score that we call test statistic is we want to compare this test statistic with the critical values that we obtained from step number 3. Remember, the critical values that we obtained from step number 3 is also a z-score or t-score. Okay. Now, from the last slide, we can see that at the 5% level and two-tailed test, the two critical z-scores are positive and negative 1.96. So if we convert our sample mean into a test statistic z-score, we can compare this z-score with negative and positive 1.96 to determine where our sample mean test statistic z-score fall. Does it fall in this rejection region or this rejection region or somewhere in the middle, so that we can determine whether the sample mean is a rare event for the given null hypothesis or not. Now, step number 5 involves the actual comparison between the test statistics from the sample mean and the critical values that are associated with the level of significance alpha. Yeah. Now, as we said before, that at 5% level in a two-tailed test, the two critical z-scores are positive and negative 1.96. Now, after we convert our sample mean into a test statistic z-score, we like to compare this value with positive and negative 1.96. If the sample mean test statistic z-score is smaller than negative 1.96, and we know that the sample mean falls in the lower tail rejection region, we would have to reject the null hypothesis. Or if the sample mean test statistic z-score is larger than 1.96, then we know that the sample mean falls in the upper tail rejection region. It is a real event for the given null hypothesis. Therefore, we will also have to reject the null hypothesis. Alternatively, if the sample mean test statistic z-score is somewhere between the negative and the positive 1.96, and then we would know that the sample mean does not fall in the rejection region. It is a non-rare event for the given null hypothesis, so we would have no reason to reject the null hypothesis. Step number 6 is to obtain the p-value that is associated with the test statistics, so that we can determine exactly how rare the sample mean is for the given null hypothesis. Now, from the last steps, we try to determine where exactly the test statistic z-score fall, this corner or this corner or here somewhere in the middle. Now, let's suppose that the test statistic z-score fall in this corner, somewhere in this corner. And to see it more clearly, we have a enlarged picture here to show this upper tail rejection corner. Now, 1.96 is the critical z-score. Our semi-mean test statistic z-score falling right here. It may be 2.58. It's larger than 1.96. So it falls in the rejection region. This particular test statistic z-score cut the corner into a smaller corner. So within this rejection corner, this particular test statistic z-score cut off a smaller corner, the orange color corner. The size of this corner may be small, 0.5%, 0.3%. So we like to use the size of this corner to calculate a p-value. So p-value is a probability number that is associated with the size of this corner. This corner is cut off by the test statistic z-score. But what if the test statistics z-score does not fall in a rejection region? For example, here on this picture, the test statistic z-score fall in a non-rejection region, somewhere between negative and a positive 1.96. It's here. So again, in this large picture, we can really see that this test statistic z-score fall outside this upper tail rejection region. It's here. Now, this orange line is where the test statistic z-score is. It's maybe 1.8. It's smaller than 1.96. So it falls outside the upper tail rejection region. They fall into non-rejection region. So now this corner, the corner that is associated with this orange line, is this corner. Now we'd like to use this corner to calculate a p-value. So the purpose of this step number 6 is to determine the size of this corner so that we can calculate a p-value. The last step is to make decision and conclude the test. Making decision here refer to we have to decide that based upon all the evidence we have so far, we have to decide whether we reject the null hypothesis or not reject the null hypothesis. After that, we conclude the test. The criteria are if the p-value is larger than alpha, we would fail to reject the null hypothesis. On the other hand, if the p-value is smaller than alpha, we would reject the null hypothesis. So we're going to see how these criteria actually played out in actual in-class activity.